Back from break. Um, we've been looking at these different circuits and showing that when it's possible, we can combine resistors in series and in parallel, and in some cases kind of go back and forth, combine some resistors in series, and then add some in parallel and add some in series, and simplify a circuit. There's other times when the circuits are more complicated, and they can't be simplified. This one, for example, I can add these two resistances together. The 40 and the 1 could be added into a 41. That's the combined resistance along that branch. And then on this lower branch, which is designated as I2, this is 1 ohm, this is 20 ohms. That would be 21 ohms. Those could be combined in series to get the net resistance. And then in this upper branch, that's 30 ohms. So this circuit has 5 resistors. That could be simplified down to just 3. So we get 3 resistors, and then we have 2 batteries. Now notice that this battery is oriented. It's trying to drive current to the left, and this battery is trying to drive current to the right. Now, what we have done, this is just an example that showed up in the slides and in the textbook. What we did was we came in and we said, this is one way of representing kind of a whole class of problems, kind of like the one that they've presented. And that would work. I mean, our formula we derived would work because we've got 1, 2, 3 branches designated by currents 1, 2, and 3. And then we have batteries, or EMFs, along 2 of those. Now, just to point out a few, what we're trying to do is match up the example that they've given us. So they have moved on to they're starting to use EMF. So for the batteries, instead of saying this is V1 and V2, they're calling it EMF1 and EMF2. I'm not quite ready to do that. I'm going to keep calling the batteries just in terms of voltage V instead of EMF. So, but those would be the 2 voltages that we would put in to the formula we've worked with. We put in the 80 volts and put in the 45 volts. Now, a couple of other things that we did differently. I labeled the currents so that the number on the current matched the battery. They've got current 2 going through battery 1, and that just causes confusion. So I called this current 1, and this would be current 2 going through battery 2, and then this was current 3, which had no battery. Okay, so that's a difference too. So if I take the example they gave me, I combine those resistors in series, then that's going to give me values for R1, R2, and R3. Now, I also changed the labeling on the currents, I1, I2, and I3, so that I didn't confuse myself. And then the other thing that's different in that example that they've given us is that the batteries are in opposite directions. Now, how could I account for the fact that instead of both batteries driving current in the same direction, parallel, they're actually opposite? Well, I could take one of the voltages and just say that it's negative. So an easy way to take what we have derived, okay, and we spent some time deriving this, this is able to be reduced down to the formula that we've derived. Let's see. So let's say that this is V1, and V1 is 80, but the way we derived it, the battery was oriented in this direction, so for the voltage here I would put in minus 45, and that should take care of it. So again, let's see, R1 is 21 ohms, R2 would be 41 ohms, R3 would be 30 ohms, V1 would be 80, V2 would be minus 45, and then it's the problem that we derived. So anyway, try using the formula, play around with it a bit. Again, this is kind of the limit of complexity with different resistors in a circuit and different loops. That's just kind of the simplest example we could come up with. There's their example again. And then they have one more example, which, let's see. This is jump starting a battery. And so here is the starter motor. And here is the weak battery that's unable to get the starter motor started. And here is the good battery that someone has come along and put in some jumper cables. The new battery needs to be put in parallel. So the new battery needs to be working with the existing battery, so they're both attempting to drive current through the starter motor. Now the weak battery is just not providing enough current, but with the good battery in place, there should be enough current. Now on this one too, we can make the connection. It turns out that this circuit also looks like the circuit that we came up with. There are two batteries working together in parallel, and then there are three resistances. So let's see how we would use the formulas we've derived with this example. So for this, what we would do is, they're calling this current 1. I like that. Oh, current 2. Hey, they've got the currents defined the same way we did. So here's current 1, current 2, current 3. V1 would be 12.5 volts. So my 12 volt battery is actually a little above and beyond. It's at 12.5. And then we have a weaker battery that has dropped its voltage, or its EMF now is 10.1. So one of those voltages we put in is 12.5, one is 10.1. The resistance, R1, is 0.02, not much resistance in that battery. Plus, you got to go in and calculate the resistance in the jumper cables. Now for the jumper cables, what they've done is they've told us they're made out of copper. Each one of those jumper cables is 3 meters long, and it's 1 centimeter in diameter. So what we can do from that is we can go back and use our resistance formula. So we can put in the resistivity of copper, look that up, put that in, put in the cross-sectional area, assuming that it's circular, that would be pi r squared, and then multiply by the length. So we can figure out, and we're guessing that the jumper cables also are designed to have very low resistance. So what we're dealing with here, in comparison with the problem before, these resistances are really small. The batteries and the jumper cables and the starter motor all have very low resistance. Now you might be thinking, hey, the starter motor requires an enormous amount of energy. The power needs to go really high for the starter motor. How do we make that happen? And for very powerful devices that need a lot of energy, we put in low resistance. So sometimes there's this feeling like, if I need a lot of power, I need a lot of resistance so that I get a lot of power. But it's actually putting low resistance that allows a lot of current to come through. And so if I want a lot of energy coming into a device, if I want a high rate of energy coming in, energy rates or powers, I want to put low resistance into these devices. And so the currents here could easily be 30 or 40 or 50 or 100 amps or something. These could be some really large values, so you can try that and see what values you come up with. But in any case, R1 is going to be the combination of, two of these jumper cables that are each 3 meters long, added onto the 0.02. Those can be added in series. The resistance along the weak path here is 0.1 ohm, and they're saying that this path that includes the starter motor, that would be R3. So R1 with the jumper cables included, R2, R3, plug those numbers in and see what you come up with for the currents going through the starter motor. And then the other item you can watch for is, if we do that, is there enough voltage here that we're actually going to be driving current back through the battery? Are we actually going to be recharging that other battery at the same time, and I doubt we are, but you could check the numbers and see if that works out to be the case. That would be an interesting set of numbers to go through. But we're going to move on. We have a couple more topics we've got to hit here in chapter 26. So what we're going to do next is we're going to introduce a circuit that has a battery. Now again, they're using EMF, and I can't draw the E's quite that fancy, so I'm going to stick with V for right now. There's an EMF due to the battery, there's a resistor, and there's a capacitor. Oh, we've never put a resistor and a capacitor together in the same circuit before. I wonder what's gonna happen. And so let's think about this. If I close the switch, the capacitor is going to charge. But because of the presence of the resistor, there's going to be a limited amount of current. Before, when we were charging capacitors, back in chapter 24, we really just assumed the capacitors would kind of charge instantaneously. You close the switch, hey, the capacitor is charged. But now we're going to actually take a look at the process itself. And we needed to introduce the concept of resistance in order to go in and analyze a circuit where we're charging a capacitor and being able to keep track of the amount of time that it's going to take. Okay, so once we've introduced the idea of resistance, now we can say, you know, if the resistance is larger, that's going to suppress the current, and that means it's going to take more time to charge the capacitor. So the capacitor is going to charge at some rate. Now, what happens when we go in and we measure voltages, so the battery has a fixed voltage, we can measure the voltage across the resistor. We can get a voltmeter out, measure the voltage here. Get a voltmeter out and measure the voltage across the capacitor. What we can see is that the resistor and the capacitor are in series with each other. And that means that the voltage on the resistor plus the voltage on the capacitor at all instants will match the voltage in the battery. The resistor and the capacitor are going to share the voltage. Now what happens here is when we first close the switch, there is no voltage across the capacitor because it's not charged. So at least initially, all the voltage starts out across the resistor. Well, as the capacitor begins to build up charge, the voltage across the resistor is going to decrease. So this is our first example of a circuit where things are changing. These are called time-dependent circuits. As time goes on, the value of the current will change. Current's not going to be fixed. And the voltages across the resistor and voltages across the capacitor will also be changing in these circuits. And so we get graphs that look something like this. What we can do for these circuits is we can go through and define what's called a time constant. What are the variables here that are determining how long it takes to charge? And so it turns out that more resistance, in the way we described, more resistance means that it's going to take longer to charge. Well, more capacitance also means it's going to take longer to charge, because if I have more capacitance, I'm going to be able to store more charge. And that means that it's going to take a longer amount of time. The resistor is still going to be limiting the current, and the current is telling us the instantaneous rate at which the capacitor is charging. So it turns out that the product, RC, is what we call a time constant for this circuit. If I take the amount of resistance multiplied by the amount of capacitance, that number, it actually has units of seconds. So we'll see that it comes out in units of time, in seconds, if we take an ohm times a farad. And what we can do is we can scale this in terms of how many time constants have gone by. So by the time one time constant has gone by, the voltage across the capacitor has risen to 63% of the final voltage. During one time constant, the voltage on the resistor, which is given by R times I, has dropped from full voltage down to 37%. And so these are exponential functions. The voltage across the resistor is dropping off exponentially, and it's approaching, asymptotically, it's approaching zero. Eventually what's going to happen is the voltage across the capacitor eventually will match the voltage across the battery, and there won't be any more current being driven. The current will just slowly drop to zero. So here's the voltage on the capacitor. Here's the voltage of the battery, right? The EMF that's given. And so what's happening is the voltage on the capacitor is asymptotically approaching the voltage of the battery. Whereas the resistor starts out at full voltage of the battery, but then it asymptotically approaches zero. And at every instant, those two voltages combined, VR and VC, add up to be the EMF provided by the battery. So those are a couple of really good graphs to see. So that's charging the capacitor. Now, where is all of this coming from? Well, what we can do is we can say that the voltage on the battery is equal to the voltage on the resistor plus the voltage on the capacitor. So we can write down the sum of the voltages are equal to the total, well, it's that same thing we talked about before. This is the voltage boost in the circuit. The battery is providing the voltage boost. And these are the voltage drops. The voltage drop for a resistor is R times I. I know they keep writing it as I times R, but it's really R times I. At least that's the way I organize my variables. And then the voltage across a capacitor is 1 over C times Q. Go back and look at this. So another key feature here, notice that everything is in series. We're looking at the very simplest type of RC circuit, one in which the battery, the resistor, and the capacitor are all in series with each other. They form just one loop. Now, what we can show is that this formula here, saying that the charge on the capacitor as a function of time behaves like capacitance times the EMF on the battery times 1 minus e to the minus t over RC. Now, what does that formula look like? I mean, I know what the exponential formulas look like, but what does 1 minus an exponential look like? So let's go back to the graphs before. It turns out this is a pure exponential drop-off. We'll see what this formula looks like too. But what they're starting off with is the charge on the capacitor. And the charge on the capacitor is proportional to the voltage on the capacitor. And this is what a 1 minus exponential looks like. So the 1 minus exponential asymptotically approaches the EMF, or the charge on the capacitor actually. And this is just the exponential itself. So again, in some sense, they're complementary functions if you add them together. So here's the formula that they derive for the voltage across the capacitor. And then what they're finding is that when I look at the exponential part of this, I've got an e to the minus t, so that would be something dropping off. And then the scaling factor, RC, will have the same units as t. So RC is what we call the time constant. And the time constant has units of seconds. And the time constant is being represented by the Greek letter tau. So just so we're clear on that, that is a Greek letter tau that is being used. Now the current, when we find out what the current is going to be at any instant, the current is going to be given by dq dt. This is how we originally defined current. And, you know, most of the circuits we've looked up until now, the current was nice and steady. And so we didn't have to take derivatives. We could just say that the current was Q divided by T. But now we want to know what the current is instant by instant. And so what we're going to do is, this is the solution to this equation. This is the charge as a function of time, I can take that formula and I can take the time derivative. Taking the time derivative of that formula gives me the current. And so I see that the current is dropping off exponentially. And the rate of drop-off is that very same time constant. So the time constant of RC is showing up in all these formulas. So let's take a look. Here's a drawing of the circuit that we just looked at. It's an RC series circuit. And what we have said is that in this type of circuit, I've written the values a little differently. I'm going to suggest that maybe this is a better way that the variables are organized, but you guys can decide for yourselves. I'm going to say that the charge on the capacitor is equal to the ultimate eventual full charge. So here is my graph showing Q as a function of time. So this should just say Q, so my graphs don't look so good. This is Q as a function of time, and here is T along here. And this is in terms of time constants. That's that Greek letter tau. Now, each of the time constants is equal to R times C, so whatever those values turn out to be. And then I've labeled the time, 1 time constant, 2 time constants, 3 time constants. And again, there's 2 type of functions we're going to be dealing with. Oh, here's the time constant right here. And then Q naught, the eventually fully charged value, is C times V, where V is the voltage on the battery. You get a V added into there. And then the current will come from taking a derivative of this function. Now, the peak current, which is at the initial time the circuit the switch is closed. So when the circuit is first turned on, the original charge the current will be V over R. So we're going to start off with the current at its peak value, and then it's going to drop off. Now, what we're trying to show here is the same thing they showed in their graphs, and that is, after 1 time constant has gone by, I can plug those numbers into those 2 formulas. The current, this is the easier function, so let's look at this one first. The current is dropping off exponentially, and that's what that lower graph is showing. The upper graph is a closely related function. It's not e to the minus t over tau, it's the complement. It's 1 minus e to the minus t over tau, and that function is this function flipped over. So it's like taking this graph, flipping it over, so that now this is the 0 line, and this is the line of maximum charge, and then those 2 graphs complement each other. If I add the 1 minus e to the minus t over tau plus the e to the minus t over tau, they add up to be 1. Okay, and then the values outside in the front are factors that are scaling and telling us just how large those charges and just how large those currents are going to be. Okay, so in your math classes, you spend a fair amount of time looking at exponential functions, and how we use them all the time in physics, in science. They just show up everywhere, and so it's actually worth spending a little bit of time seeing how they work. And so, just an exponential drop-off like this, after 1 time constant, it has dropped to 37%. After 2 time constants, and you can put the numbers in, this is like e to the minus 1, e to the minus 2, e to the minus 3. And that goes 37%, and then 37% of 37% is 14%, and 37% of 37% of 37% is about 5%. So there's a little rounding here. Meanwhile, as far as the capacitor being charged, 1 time constant puts us at 63%, 2 time constants is the complement of 14, that's 86, and 3 time constants is the complement of 5, it's 95%. And at this point you might be thinking, well, wait a minute, does the capacitor ever fully charge? And mathematically, what you would say is that this function is just always asymptotically approaching that final value. But once you've had 10 or 20 time constants go by and you plug the numbers in, you're going to find that we are so very close to that asymptote that essentially we have arrived. Once you're accurate to within 1 electron charge, you can treat the capacitor if it's fully charged. Once it's 0.9999999999999, then you go, yeah, it's fully charged. And that's what happens in these circuits. Now, this is a couple graphs showing how the charge is varying as a function of time and how the current is varying as a function of time. And we've looked at it in some detail, and it's worth staring at it and kind of talking yourself through this. This is the charge and the current. What do the voltages look like? And remember that the voltage across the capacitor will be proportional to the instantaneous charge. So the voltage across the capacitor will look just like this graph, but the vertical axis will be scaled in volts instead of in terms of coulombs of charge. Similarly, the voltage across the resistor is going to look just like this graph. It's going to look the very same. It's going to have time constant, 2 time constants, 3 time constants. The only difference will be, instead of this being the current, this will be the voltage across the resistor. Okay, so let's take a look at those graphs and see what they look like. Oh, there they are. So the peak voltage across the capacitor is going to be given by Q naught over C. The peak voltage across the resistor is going to be given by R times I naught. And so what we've done is we've taken those very same formulas, the 1 minus e to the minus t over tau. When we were looking at charge, it just had Q naught, but now we're going to take the charge, divide by C, and that turns us into voltage. The formula we had on the previous slide for current, when that gets multiplied by R, it becomes the voltage across the resistor. So what we've shown is, if I take the voltage across the capacitor, this formula, the whole thing right here, and I add on the voltage across the resistor, this whole formula here, we can go through and show that those two items added together combine to equal V naught at all times. And all through all of this, RC is the time constant. Okay, so I hope this is kind of interesting now to have these circuits where things are happening with respect to time. So this certainly means drawing graphs are in your future. So make sure that you are clear how to draw these exponentials and to draw them with reasonable clarity, so that if a problem comes along on a midterm or on the final or something, asking to show charge on the capacitor, current through the circuit, voltage across the capacitor, voltage across the resistor, you're familiar with how to draw those graphs, scaling the time axis and then scaling the vertical axis for whichever of those 4 quantities you're looking for. Okay, here is problem, so let's go ahead and take a look at this one. Looks like the circuit we've been talking about. Again, they are using this fancy E for what's called script E for EMF, but I'm going to keep using V for voltage. Ooh, and they even have an S for switch. Let's see, so the capacitor here is at 300 nanofarads, and the resistance is at 20,000 ohms. That's a lot of resistance. And the EMF here, the voltage on the battery, is 12 volts. So they want to find the time constant. Okay, I can do that. It's R times C, right? And then the maximum charge that the capacitor will eventually acquire. What's that asymptotic value for charge? And then how much time does it take for the charge to reach, ooh, there you go, 99% of being fully charged. And then the current I, when the charge is, that's a lot of questions. Okay, we better get to work. So I know I'm supposed to read the problem carefully. But we'll go back and read. I'm gonna write down what was given. There's a lot of stuff going on here. Here is the capacitance that was given. I switched over into nanofarads instead of using the decimal form of that. And then the resistor is 20,000 ohms. That's a lot. Voltage is 12. Okay, time constant is R times C. No big deal, right? So the 20,000 means I have to, the kilo means I have to keep track of the 10 to the third. The nano is 10 to the minus 9. So when I multiply these numbers all together, the time constant is still pretty quick. So it worked out to be just 6 milliseconds. And I think it's good to see milliseconds here, because often when students see that, they go, why do we have units of meters, seconds? And they're not meters, seconds. These are milliseconds. Milli is 10 to the minus 3. So that's what we've got, is 6 milliseconds. So these time constants are happening fast in this circuit. And then the second thing they say is, what's the eventual full charge on the capacitor given this voltage and this capacitance? So the eventual full voltage. Now notice I'm calling this Q naught. And in this example, and in other circuit examples that that we're going to be looking at, I tend to think of the peak value. Well, we've used that before. So the Q naught here you can think of as what's the eventual highest value that we're going to reach. It's not the initial charge, it's the final charge, the eventual asymptotic value. C times V is giving, as they put the numbers in here, 3.60 microcoulombs. So you've got to watch units carefully here. And what you're noticing, I hope, is that there's a lot of new units that are being thrown at us. And so practice playing around with these units. So for example, an ohm times a farad, we can go through and show that those are seconds. So, you don't have to tell your friends now, hey, I'll be there in 10 seconds. You can say, I'll be there in 10 ohm farads, right? Because that's equivalent units. And then you got to pay attention to these prefixes. There's a kilo here, there's a nano here, there's a nano here. And then every time you get past 1,000 of something, like here, the 12 times 300, well, that's going to give me 3,600. Then I can switch from nano back into micro. And that's kind of standard for working with circuits. We tend to use whatever prefix is most convenient. And so what we're trying to do is keep, 3 significant figures, no reason to go past the decimal. So we want to keep a few digits to the left of the decimal, and then we use whatever prefixes allow us to do that. Okay. Part C, was asking how much time is going to be required to reach 99% of the final value. And so looking at my equation here, I can see that this is a question asking about how much time. Time is included in this part of the formula. What I'm really asking for is, when does this stuff inside the parentheses equal 0.99? And so I can take this formula, set it equal to 0.99. And what that tells me is, when the 1 minus exponential equals 0.99, the exponential itself equals 0.010. So I'm looking for when this part has reduced, the exponential part itself is reduced all the way to 0.01. So I can take this formula and I can take a natural logarithm on both sides. So if you haven't played around with logarithms for a while since your math classes, start playing around with logarithms. If I take a logarithm on the left side, that undoes the exponential, and then what I'm left with is an ln on the right side. And so that formula becomes minus t over tau is equal to the ln 0.01. So, and I'm sympathetic about logarithms and exponentials, logarithms in particular. Every time I come back and run into logarithms, it seems like I have to remind myself how logarithm functions work. But what we're most important to us here is to be able to take these equations and solve them reliably. So what this turns into is the time required is equal to the time constant times the logarithm of, now this was the logarithm of 100th, but it had a minus sign here. To get rid of the minus sign, we can flip logarithms. So instead of writing this as the logarithm of 0.01, which will give me a negative number, I could just flip that number and write it as its inverse, and that will remove the minus sign for me. And sometimes I like to do it. I like to get rid of minus signs as soon as I can. If I've got an algebraic expression with minus signs here and there, I start to worry a little bit that I'm going to lose track of them. So anyway, it's one of those tricks that you can use if minus signs make you a little nervous. And then I just plug the numbers in. Do we know what the time constant is? It's 6 milliseconds. And so the time I ended up with was 27.7 milliseconds, which is 4.6 time constant. So I can always get the answer in terms of time constants first. And does that make sense? 4.6 time constants? Let's go back and see. We had some benchmarks that we had kind of written out there. So we're trying to hit 99%. So what we had shown before was, oh yeah, one time constant is at 63, two time constants is at 86, three time constants is at 95. It's going to take more than three time constants. Turns out it takes 4.6 in order to get to 99% of that ultimate final value. Okay, so these are all good examples for you to be going through. We are going to, we're interested in being able to solve these types of problems. Now, there was also a D, E, and F on the problem, and at that point I'm thinking, really? Did they need to have D, E, and F too? On D, E, and F, they were asking what happens when the current has dropped to 1/2 of its value, and at that very same time, when the current has dropped to 1/2 of its original value, the capacitor will be 1/2 towards its final charge. Remember, those two numbers are always going to be complement. Together they'll add up to 1. And so if I've dropped to 50% here, this one has risen to its complement, which is also 50%. There's the circuit again. These are the formulas for Q and I. And so the ultimate current that we're going to reach is V divided by, the starting current, the initial current that we will have. It's going to start off at V over R, and that's going to be 600 microamps. So it's not a lot of current. It's only down there in the microamps. We are looking for how much time has gone by when we hit 50%. Now, from what we've been looking at, hitting 50% will happen even before the first time constant. The first time constant is going to drop us down to 37%, right? One time constant is going to take us past. And so what we can find, using the same formulas we used before, is that when we reach 1/2, when I is equal to 1/2 I naught, that t is equal to tau, the time constant, times the ln of 2. So this time we're looking at where it's dropped to 1/2, not 1/100th. And so this is going to be an ln of 2. That's 0.693 time constants. And that, in terms of time, that's 4.16 milliseconds. So that is how much time will have gone by when the current has dropped to 1/2. And then at that point, the peak current, they ask about the peak current. The peak current is 600 microamps, so we solved that up there. And then what's happening at that particular instant, the 1 minus t over tau and the e to the minus t over tau are going to be complementary values. And so, what did F ask? I think F changes the numbers again. Yeah, it did. So D was based on the 50-50 split and that exponential. But on F, they come back and ask about the charge when the current is at 20% of peak value. Well, if the current has dropped to 20%, then the charge must have risen to 80%. So we can use that sense that these two functions are complementary. We don't have to go in and do a lot of math. If they're willing to tell us what fraction of the peak current we have dropped to, we can just write down the complementary number and say, hey, that's how much charge. It will be at 80% of maximum charge. And the maximum charge we had calculated on the earlier page. Okay. So that's how these circuits work. Now, what about power? This gets a little complicated. I'm going to go through it pretty quickly. But what we can do is very systematically go back and use the power formulas that we have developed. Now, I don't think they ask us about this, so I think we're kind of out on our own. We're being overachievers with this. But here's what the circuit looks like. Here's the capacitor, here's the resistor. We found out what the current is as a function of time. We found out what the individual voltages are on the capacitor and on the resistor. And now what we can do is we can go through the circuit one at a time, one component at a time, and identify what's the power in the resistor, what's the rate at which the resistor is generating thermal energy. That's what resistors do with the energy that comes their way. So at what rate, now the rate turns it into a power, energy per time. So at what rate is the resistor generating thermal energy? And if I take the voltage function specifically for the resistor and multiply it by the current function, now everybody's got the same current. So everybody's going to have the same function representing the current. That gives me V naught I naught with two factors of exponential drop-off. So the power in the resistor is going to be dropping off doubly exponential. What about the power in the capacitor? What does that even mean? For a capacitor, capacitors do not thermalize energy. Energy that comes their way gets stored. So capacitors store energy, and they store energy by storing positive and negative charges on their plates. They have a lot of charge on their plates. And so we can take the voltage on the capacitor, which we've written down that function, and the current, which everybody's got the same expression for their current. That gives us V naught I naught. Now this one is one factor of exponential drop-off times one factor of exponential approach to a final asymptotic value. For better or worse, that's what they are. What this function looks like when we graph it is initially the capacitor is storing energy not so fast at first, but then as it begins to build up more and more charge, there's more and more a higher rate of energy storage, but then the current begins to shut down. And so when the current shuts down, so does the power for the capacitor. Now, an interesting feature of calculus is that we can measure the area under these curves. The area under the power curve, this is power versus time, and the area underneath that will be the total amount of energy thermalized by the resistor during the charging process. The area under the capacitor will be the total amount of energy that's been stored in the capacitor during the charging process. So the areas under these power curves are total amounts of energy. And that's what we've shown here. So we're saying that the energy that gets thermalized in the resistor can be calculated by integrating the power during the entire charging process. And for the entire charging process, we can take limits from 0 to infinity. If we integrate that function from 0 to infinity, what we find is, and carry through the calculations, we find out the total amount of energy thermalized by the resistor is 1/2 CV squared. So it depends on the voltage of the battery, it depends on the capacitance. An interesting feature here is, it doesn't depend on the resistance. So if I put a little bit of resistance in there, the capacitor charges fast. If I put a lot of resistance in there, the capacitor charges more slowly. But either way, either the low resistance resistor or the high resistance resistor will end up thermalizing the same amount of energy. So there's no, is this a no free lunch example? I don't know. Anyway, what it's saying is I don't get to charge my capacitor without having some of the energy get turned into thermal energy along, even by using a really, really small resistor. It doesn't help. I still end up thermalizing that much energy. If we do the same calculation with the capacitor, what we find is the very same number. We find out that the amount of energy coming out of the battery has to be double what we want to eventually use to charge the capacitor. Because if I want to get 1/2 CV squared energy stored in my capacitor, I'm going to end up thermalizing 1/2 CV squared in my resistor during that process. Okay. Now we can also go back, I don't think I did that, we can also go back and do P is equal to V times I for the battery. Now for the battery, the voltage is fixed at V naught, and I can multiply by that expression, and we can show that the energy, or the power coming out of the battery at each instant, combines to these two values. So the power graph, the power for the battery, the graph would be the sum of these two. And that'll tell you, so whatever energy left the battery, we can account for where it went. It either got thermalized in the resistor, the energy went into thermal energy, or the energy is stored in the capacitor. Half of it will be stored in the capacitor. Let's look at discharging a capacitor. So we looked at what happens when we charge the capacitor. What happens if we start with a capacitor that's already charged, and then we allow it to discharge through a resistor? Well, we find out in this case that we end up with the very same functions. The charge will drop off exponentially in this example. So I'm going to start with this much voltage on my capacitor, and that voltage will drop off exponentially. The charge will drop off exponentially, the voltage will drop off. And again, if I've got the very same capacitance and the very same resistance, the time constant for that discharging process will have the very same value. I'll have the same value for discharging that I had for charging. Okay. We can take the formula that we wrote down for the charge, we can take a time derivative and show that the current is also dropping off exponentially. So when we discharge, both voltage, everything's dropping off exponentially. The charge is dropping off exponentially, the current is dropping off exponentially, both voltages are dropping off exponentially. Now, they've put a minus sign in here, and I would prefer leaving that out. So when the capacitor discharges, I actually prefer seeing that the current now is going in the opposite direction. So when we charge the capacitor, we think of that current as being in the positive direction. But when we discharge it, the current's got a reverse direction. They've put a minus sign in here so that that stays positive, but I think that means we miss something. First of all, why should I be changing the definition of current? I should use the same definition of dq dt throughout, not with a minus sign. And then if I'm discharging, I'll get a minus sign on the current, and that'll tell me that the current now has reverse direction and the capacitor is discharging. So here's the whole setup for this. So there's a picture of what the circuit would look like where I'm charging the capacitor. I close this switch. I got two switches. Here's a switch, here's a switch. I close the first switch. That will charge my capacitor. And I've got the capacitance and the resistance combined together. So once the capacitor is charged, I open that switch, and now the charge is there. Then I can close switch 2 and allow the capacitor to discharge. And during the discharging process, the charge is going to drop off exponentially. I didn't put the time constants in, I should have done that. And then the current will have reverse direction. So as I was saying, I prefer, here we go. Here's what the solutions look like. Here's the charge as a function of time. And then if I just flat out take a time derivative, I'm going to get a minus sign. That tells me that the current now has reversed directions from what it was before. When it was charging, the current was going through the middle region this direction. When it discharges, it goes back the other way. The positive charges begin to leave, and the negative charges are going to get canceled. The time constant is the same. And again, where all this is coming from is the voltage boost is equal to all the voltage drops. That was for charging. When we discharge, there is no voltage boost. There's no battery. And that means all I have are voltage drops. And that means one of the voltage drops has to be minus. So even though we think of a resistor and a capacitor as providing voltage drops, in this case, it's the capacitor that the current ends up going in the opposite direction and discharge using the energy in the capacitor. Now, by the time we've completely discharged, all the energy in the capacitor has been thermalized. So let's think about this. When we charged the capacitor, half of the energy that we needed went to charging the capacitor, but we also had to put half of that energy into the resistor. So if I'm going to store 10 joules here, then I'm going to thermalize 10 joules here during the charging process. So the battery's got to provide 20 joules. Now when I discharge the capacitor, all 10 joules that were stored here are going to get thermalized. So at the end of the day, we've converted all of the electrical energy into thermal. Okay, so here is a conceptual example. I like this. So here's the battery. Oh look, they went back to using V0. Excellent. I like that. So here is V0, those fancy E's. I just have a hard time with those. Here's my switch. There's the capacitor. Now what we know, this is just an RC circuit. It's just that in this case, the R specifically is a light bulb. And that means, let's see, what's happening with the current there. When we first close the switch, the light bulb is really bright, and then exponentially it drops off. What we would see, in fact, we have solved for this. The brightness would be proportional to the power. So the power through the resistor would be doubly exponential drop-off. And so that power is going to start off at the light bulb is going to start off at being its very brightest that it's going to get, and then it would drop off based on the time constants. And if the time constants is long enough, then we can actually observe this. The time constants we saw in our problem were so rapid, we wouldn't necessarily pick that up. Okay, let's talk a little bit about ammeters and voltmeters. So the RC circuits that we've talked about here, those are important. So make sure you're going through the RC circuits and understanding the charging process and the discharging process, and we've gone into some detail there. I've tried to be as systematic as possible. So let's talk a little bit about ammeters and voltmeters. Here's a circuit. I've got a battery, I have a couple resistors. I would like to be able to measure the current. I would like to be able to measure voltages. Now the current, for this one loop circuit, the current is going to be the same everywhere. And that means I can put the ammeter in wherever I want. If I put the ammeter here, if I put the ammeter here, if I put it here, if I put it here, it's going to have the same readings. I could put a bunch of different ammeters in the circuit, and I'm expecting they're all going to read the same value. Now, I don't want these ammeters to disrupt the circuit. So what I do is I design the ammeters so they're very, 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 really very low resistance. So an ammeter is designed to have low resistance to it. And that makes an ammeter kind of vulnerable or susceptible to being damaged, because if by accident I attach, say, a battery, if I attach an ammeter to a battery by mistake, it'll drive so much current through it, it'll damage the ammeter. The ammeter probably gets ruined. Now if I'm trying to measure voltage, what I'm trying to do is off to the side of the circuit, I don't have to disconnect the circuit. Notice with the ammeter, I got to take the circuit apart and integrate the ammeter right into the loop so it can measure the current. But a voltmeter can measure voltage from the side. So the voltmeter just makes contact with two places. In this case, the voltmeter has been set up to measure the voltage across, specifically resistor 1. If I wanted to measure resistor 2, I would disconnect the voltmeter here and connect it at B and C. If I wanted to connect the voltage across the battery, I could connect the voltmeter from A to C. Voltmeters are designed with a lot of resistance because we want the circuit to continue behaving as it was when I connect the voltmeter, and this parallel path, we want to prevent current from taking the parallel path through the voltmeter. We don't need a lot of current to be able to do our measurement. Okay. And so here's an example with the ammeters and voltmeters, and we are not going to worry about that. That's one that you can look at. So for us, chapter 26, and I think that's it. So we're going to wrap things up here. The big topics for us are being able to combine resistors in series, being able to combine resistors in parallel, being able to simplify circuits so that we can combine things in series and parallel, and then do some very, very simple loop type of equations, and then those RC circuits. So the RC circuits, and it's kind of represented with our time constant here. Those are the big topics for the chapter. So if you guys have questions, it's a moderately challenging chapter. So any questions come up, let me know. Stop by office hours, contact me, and we'll get those questions looked at.